Moving on to Chapter 6, Part C. In Part C, we're going to focus on the capital asset pricing model and the security market line. Recall that we ended Part B decomposing standalone risk or total risk into two components, market risk and diversifiable risk. Rational investors are expected to hold a well-diversified portfolio, virtually eliminating firm-specific risk. That leaves only market risk as relevant. So how do you measure the amount of market risk for a particular security or a portfolio? CAPM, developed by William Sharpe, answers that question. And the answer is beta. Building up to beta. WI is the percentage of dollars in the portfolio invested in stock I. Sigma M is the standard deviation of the returns on the market portfolio. Sigma I is the standard deviation of the returns on stock I. Rho IM is the correlation between the returns on stock I and the returns on the market. To measure the contribution of each individual asset to the riskiness of a portfolio, we can use the formula above. The key point is in bold type. Beta measures the impact of an individual stock on the riskiness of a portfolio. Given the formula, if the correlation of stock I with the market is higher, then beta is higher. Or if the standalone risk of stock I is larger, beta is larger. The beta of a portfolio is simply a weighted average of the betas of the assets in the portfolio. Same formula as for the expected return on a portfolio, but we're weighting beta instead of return. The standard deviation of a well-diversified portfolio can be approximated with the formula on this slide. The implication is clear. If the beta of the portfolio is greater than 1, the standard deviation of the portfolio will be greater than that of the market, meaning the returns of the portfolio are more volatile than those of the market. Market goes up 10%, portfolio goes up 12%. To measure the contribution of each individual asset to the riskiness of a portfolio, we can use this equation. The key point is again in bold type. Beta measures the impact of an individual stock on the riskiness of a portfolio. We can break down required return into two basic components. Return for the time value of money, the risk-free rate. Return for risk, the extra return above the risk-free rate to compensate investors for investing in a risky asset. RP sub M, the market risk premium, is simply the expected return on the market minus the risk-free rate. The risk premium for an individual stock is defined as the market risk premium times beta. The security market line, SML, puts all the pieces together. It defines the required return on an asset or portfolio as made up of compensation for the time value of money, the risk-free rate, compensation for the additional risk of asset I, equal to the market risk premium times the beta of asset I. Summarizing, the required return on an asset depends on beta. The part of the risk of a portfolio due to a specific asset depends on the beta of that asset. We need two variables to calculate beta: the covariance between the returns on the asset and the returns on the market, and the variance of the returns on the market. Given those two pieces of data, Formula 613 and 614 provide formulas for beta. However, we're going to use equation 6.8 on the following slides. Now that we've explored the theory behind CAPM and the security market line, let's apply it to our sample companies, Blandy and Gourmange. First, we need the correlation of Blandy's returns with the market, 0.481. Applying equation 6.8 using Blandy's data, we arrive at a beta of 0.60, significantly less than the market-defined beta of 1. Once we have a beta for an asset or portfolio, we can apply the capital asset pricing model, CAPM, to estimate the market required return. Assuming a risk-free rate equal to 4% and a market risk premium of 5%, substituting into CAPM yields a required return on Blandy of 7%. Betas for Gourmange, 1.3, and the market, 1, are given so we can compare required returns. Clearly, larger beta, large required return, higher risk. To estimate beta from historical data, we could run a regression of the returns on the asset against the returns on the market. The slope of the resulting line is beta. Using Excel, we can plot the trend line and see the resulting equation. Conveniently, the resulting beta is 0.6027, very close to our earlier calculations. Note the scattering of the data points and the relatively low R-square value of 23%. Excel also has a slope function, which will find beta for you. Beta estimates are provided by many analysis sites, including Yahoo Finance and Value Line. Be aware that the variables in the CAPM equation are not static. The risk-free rate changes, as does the market risk premium, depending on the degree of risk aversion in the market at any time. If the risk-free rate increases but the market risk premium stays constant, the SML will shift upward, since the risk-free rate is the y-axis intercept. If the risk-free rate remains constant but investors become more risk-averse, then the market risk premium increases. The line will ratchet up, taking on a steeper slope. To close out this section of Chapter 6, let's apply what we've covered to a portfolio of Blandy and Gourmange. First, we need the weights, the percentage of dollars, of each asset in the portfolio. The calculations are shown on the slide. 70% Blandy, 30% Gourmange. Applying those weights to the given betas, we arrive at a beta of 0.81 for the portfolio. Finally, using CAPM SML equation, we can find the required return on the portfolio, 8.05. This ends Part C of Chapter 6. In the final segment of Chapter 6, we'll look at performance measures, market efficiency, and equilibrium.